The question we want to address is whether or not a reaction will go. So let's make some observations. I have here some lithium chloride, some potassium chloride, 2 beakers, and some water. And I'm going to try to dissolve these ionic compounds in water. And there are 2 questions I want to answer. First, does the process go? And second, is it exothermic or endothermic? So, I'm going to start by squirting some water in here. That should be enough. And I also have a thermometer that I'm going to put in here just to keep track of the temperature. So we'll put some solid lithium chloride into this beaker. Put in a few scoops here. Maybe one more. And we'll start stirring. The question is, does this dissolve, and is it exothermic or endothermic? Give it 30 seconds or so of stirring. I want to be careful not to hit the thermometer with my stirring rod. And of course, you never stir a solution with a thermometer. That can certainly lead to disaster. And actually, I can feel this warming up. Almost all dissolved. Tell you what, let's stop here and look at the thermometer. And in fact, the temperature has gone up to 29 degrees C. So, I felt the beaker heat up. I determined this was an exothermic process, and we measured a temperature rise. But you might be saying, wait a minute. The ionic compound and the water mixing together, isn't that the system? And if the system increases its temperature, didn't it absorb energy? Doesn't that make it endothermic? Well, no. We have to think a little bit harder about what the system really is. The system is the individual ions that start bonded together, that come apart, and individually get surrounded by water molecules. That's the process. That's the system. And that process gives off heat, in turn heating up the rest of the water, the beaker, and ultimately my hand. This hints at a way that maybe we could quantify this energy transfer process. If we carefully measured out the amount of lithium chloride we used, and carefully measured out the amount of water we used, and took care to insulate that system, not letting the process heat up the beaker and my hand and the air around it, but insulate that system, we could actually quantify the amount of heat that's transferred. And that is actually an established process called calorimetry. Again, I've got my water, and this time we're going to put in some potassium chloride. And the water is starting out at 22 degrees C as it did before. Put in a few scoops of potassium chloride. Maybe one more. Good. And we'll go ahead and stir this. Now the lithium chloride I could feel heat up when I was stirring it. This one feels like it's cooling down. Yep, it's definitely getting colder. This is a process that goes, that salt dissolved, but instead of being exothermic, it's endothermic. If I check the temperature, it's down to about 18 degrees C. So we've looked at 2 processes. Lithium chloride dissolving in water and potassium chloride dissolving in water. They both go. Very similar processes, yet one is exothermic and the other is endothermic. That's not something that we could predict ahead of time. We can summarize the results as follows. For each salt, we can write a balanced chemical equation. Solid lithium chloride goes to aqueous lithium ions and aqueous chloride ions. Solid potassium chloride goes to aqueous potassium ions and aqueous chloride ions. We found that both processes will go. However, the first process is exothermic while the second is endothermic. The first takeaway message is that you cannot tell whether a chemical reaction is exothermic or endothermic simply by looking at the balanced chemical equation. That is something that needs to be determined experimentally. Second, the fact that a process is exothermic or endothermic does not determine whether it will go. We'll find that enthalpy change does play a role, but there is another factor that we will need to explore. Let's make a couple of more observations from videos on the internet. The first has to do with this reaction: hydrogen gas plus oxygen gas reacting to form water. The man is holding a long stick that has a flame at the end, and that flame is going to ignite the hydrogen that's in the balloon. So let's watch. What you notice is that the reaction starts where the flame started out, and then it spreads through the entire volume of the hydrogen. That certainly appears to be a reaction that goes. The second reaction is the reverse reaction, which is accomplished by the electrolysis of water to form hydrogen gas and oxygen gas. We'll see this video again in its entirety when we talk about electrolysis later in the course. Here, Dr. Petrovich has two tubes that are filled with water and a platinum electrode at the bottom of each one, and an energy source, which is a 9-volt battery. And what we'll notice is that the reaction does not go until she connects the battery leads. In that case, gas starts bubbling off of each electrode. After the reaction goes for a while, what you'll notice is there's twice as much gas in the left-hand tube as there is in the right-hand tube. The gas bubbles have gone up to the top and been collected at the top. And of course this makes sense given the fact that the balanced chemical equation predicts 2 moles of hydrogen for every 1 mole of oxygen. The important thing to notice here, though, is that the reaction keeps going until the battery is disconnected. But once the power supply is removed, the bubbling stops. This reaction will go, but only with the constant input of energy. At this point, asking whether a reaction goes is not a good enough question. We're going to introduce a more technical term. A spontaneous process is the one that, once started, will go without continuous outside assistance. While the balloon with hydrogen needed to be lit, once it started, it kept going. It did not need continuous outside assistance to keep going. So the first reaction is spontaneous. The second reaction needed a constant input of energy to keep going. The reaction stopped when the battery was disconnected. So we would say that the second reaction is non-spontaneous. We'll talk about the spontaneity of reactions on the upcoming pages. But how can we tell if a reaction is spontaneous? What are the criteria for spontaneity? To answer that question, we need to introduce a quantity called entropy.